Here are a couple examples of doing Fourier series. The first one is, write y equals sine squared of kx as a Fourier series. You might look at this and say, look, it's just a sine wave, right? Well, it's already a Fourier series. But no, it's not a sine wave, it's sine squared. That's a different function. Now, knowing what I know about what happens when you square a sine wave, I can actually get to the answer pretty quickly. It turns out, so here I've plotted in blue a sine wave, and then in purple here is the same wave but squared, right? So at 0 they're both 0, they both go up to 1, they come back down to 0, but the squared one now goes up again. And it turns out if you square a sine wave, what you get is something that oscillates sinusoidally, but it doesn't oscillate between -1 and 1, it oscillates between 0 and 1, all right? So it oscillates about 1/2, and it oscillates at twice the frequency. And also notice that whereas the sine function is an odd function, if I square something, I always get an even function, right? So it's an even function. So I look at this and I say, well, look, this is just a cosine wave. It starts negative rather than positive, right? So it's a negative cosine wave oscillating at about 1/2. So I could just write down and say, look, this is equal to 1/2 minus 1/2 cosine 2kx. That is a Fourier series, right? It's just a sum of sines and cosines. Here's my cosine of 0 frequency, and then I have a cosine with a wave number of 2k. All right? So that's what I should get. I could just write that down and be done, but let's actually work through the problem, do the Fourier series mechanics. All right? So the first thing to note is that sine of kx has a wavelength of 2 pi over k, right? Which means the wavelength, kind of the fundamental wavelength over which my sine squared function repeats is half of that, right? So my sine function repeats from here to here, but sine squared repeats in half that distance. Which means that the wave number, kind of the fundamental wave number, is twice the fundamental wave number of sine kx, all right? So k naught, the fundamental wave number with which this sine squared function repeats is just 2 times the k in that equation right there. So now with that, I'll go ahead and do my integrals. I'm going to write y of x as a sum of sines and cosines. That's my Fourier series. First, let's look at the ace of n terms, all right? So here's the equation right out of the book that I plug in. I've kind of modified, right? You can basically, in your book, we have an equation that looks like this, but it has different limits, but those limits turn out to be the same thing as 0 and lambda naught. All right, but I'm not going to actually do this integral. I'm just going to be clever. I'm going to look up here and I'm going to say, look, my function is even, sine is odd, therefore I know that all of my a sub n's are going to go to 0. So no a sub n's. If I calculate b sub 0, I just have this integral right here, which turns out to be the average value, right? b sub 0 is always the average value of your periodic function, and the average value of sine squared was 1/2. So I can either do that integral or I can just know it's 1/2 and write it down. Now for b sub n, right, here's the integral I do. I just plug my function in right here and I do the integral. All right, I looked this up. I have Mathematica solve what sine squared times cosine is equal to, and it gives me this thing right here, and I evaluate it between my limits. Before I do that, I'm going to note something, all right? So this 2k right here, that's the same thing as k naught, right? So we can combine those here. So 2k becomes k naught, and just doing some algebra to get from here to here, replacing my 2k's with k naughts, it looks like this. Now when I go to plug in my limits right here, when I plug in 0, all of these sine waves are going to go to 0, right? But when I plug in lambda naught, right here, what is lambda naught? It's 2 pi over k naught, or k naught is 2 pi over lambda naught. So when I plug this in here, n k naught lambda naught is just going to be n times pi over 2. Or sorry, it's going to be n times 2 pi. All right? So that's going to go to 0, right? N times 2 pi, for any value of n, that's going to go to 0. I get the same thing here, and I get the same thing here. They all go to 0. So, what the heck? All right? Now, it turns out this problem is a little more subtle than most of the Fourier series problems you'll work in this class. You look at this and you realize all of these terms go to 0 when I plug in lambda naught and when I plug in 0. But then you look at this one right here and you say, well, if n is equal to 1, for n equals 1, I'm also dividing by 0. So this term, for any n that I plug in, this one's going to go to 0 and this one's going to go to 0. But this one is special. At n equals 1, I have 0 divided by 0. So that doesn't necessarily go away. So I know all of my b sub n's go to 0, except possibly the n equals 1 one. So n equals 1, I have to take the limit here as n goes to 0 and see what happens when I take that limit. So I'm going to take the limit of this. All right? What I'm going to do to figure out that limit is I'm going to use L'Hopital's rule. Remember, the limit of something over something is equal to the limit of the derivative of something over the derivative of something. I'm taking my derivative with respect to n now, not x, right? Because I'm taking the limit as n goes to 1. And when I do that, here's the same function right here. I take my derivative, the sine becomes a cosine, and this just becomes this. All right, and I just do some algebra, and I find that b sub 1 equals negative 1/2. All right, so my Fourier series is basically 1/2 minus 1/2 cosine k naught x, right? I have b0 was 1/2, b1 is negative 1/2, so there's my Fourier series. And remembering that k naught is 2k, I get this, and that's exactly what I said it was supposed to be. So this worked out. I'm happy. Our next problem, let's write this function as a Fourier series. So here we've got a function that starts at 0 at, let's see, so here's t over 2, so here's t over 4. So at t over 4, negative t over 4, I'm at 0. It ramps up to h when I get to t over 4, and then it goes to 0 until I get to 3t over 4. All right, so that's my repeated function. Well, when I do my integrals, this is not something I can represent analytically easily. All right, and that's one of the great things about Fourier series is I can take a function like this that I don't have a, I can't think of an analytical expression for something. It's discontinuous and such. I can write this as a sum of sines and cosines, and suddenly I have an analytical way to write this. But in order to do the Fourier series, I need to start with some sort of analytical way to write this so I can plug it into my integrals. So what I'm going to do is I'm going to break this up into pieces. Here's a piece, and here's a piece. All right? I'm going to break my function up into pieces, and over those pieces, I know how to write the function. So when I do my integrals, it says in the book that I need to integrate from 0 to 1 period, right? This function repeats itself as I go from 0 to t, all right? But it turns out because everything is periodic in your function, in your integrals, I can start anywhere and just integrate by 1 period. So for this problem, I'm actually going to start at negative t over 2 and integrate to t over 2, all right? The fundamental period of my wave function, the period over which it repeats itself, is just t, all right, as drawn on the graph, which means the fundamental angular frequency is 2 pi over t. All right, so let's go. I'm going to try and write this as my Fourier series here. I need to know what my function looks like in these different regions. So I look at this. This is what I get. If I go from negative t over 2 to negative t over 4, that's this region right here. It's just equal to h over 2. And from t over 4 to t over 2, also it's equal to h over 2. And this thing here is just a straight line. So you sit down, you figure this out, and you realize, in the middle here, from negative t over 4 to t over 4, it's just a line with an offset. All right, so there's my function for those 3 regions. And then I'm just going to do my integrals from negative t over 2 to t over 2, and I'll plug these in for the various bits of my integrals. All right, so first let's do b naught. Remember, b naught is just the average of the function. It's just the integral of 1 over t naught times the integral of that function. All right? I'm going to break this up into 3 pieces. So I have 1 over t naught, and then I'm going to integrate from negative t over 2 to negative t naught over 4. And for that region, my function is just h over 2. And then I'm going to integrate from negative t naught over 4 to t naught over 4, and that's where my function is aligned. So I plug in that function right here into my equation. And then I have another integral that goes from t naught over 4 to t naught over 2, and again here it's just equal to h over 2. Doing the integrals, plugging in the limits, it turns out b naught is just h over 2. All right, now I can go and I can plug things into the other integrals as well, but before I do that, I'm going to do something tricky. All right? Notice I've got this function here. Instead of summing from n equals 0, I'm going to sum from m equals 1 and pull out this constant term b naught. All right? Now I'm going to take it to the other side. So if I take the function y of t minus b naught and write it as a Fourier series, it will have no constant term because I already got rid of the constant term. And it looks like just the Fourier series of y without the b naught. So in other words, all the a sub n's and b sub n's will be the same for this function or this function, right? So basically, once I've subtracted off that offset, I'm left with this function right here, and the higher n coefficients will be the same as for my original function. This function's easier to work with because it's got zeros here, all right? And so I'm going to use this function instead of the one I started with to get my higher n's. If you want to, just plug in this equation, this stuff right here, into your equations and churn through it, but you'll get the same thing if I do this function and then just remember there's an offset. Okay, and it makes my life easier. First of all, because from here to here and from here to here I don't have to do an integral because this function is 0. Also, once I take the offset off, I mean, if I look at my original function, it's not an even function, it's not an odd function. I expect to get both a's and b's. But once I subtract off the offset, I have an odd function. And it occurs to me, I do have this one b sub 0, but once I take that into account, once I take that off, I'm left with an odd function. So that means all of my other b's are going to 0, and I just have to find my a's. All right? So let's find what the a's are, and I'm going to use this other function here. All right, so I plug my function in and I do this integral, but when I plug the function in, remember, from negative t0 over 2 to negative t0 over 4, my new function, my adjusted function, is 0. And from t0 over 4 to t0 over 2, my adjusted function is 0. So now I just have to integrate from here to here, and here's the function when I subtract that offset off. All right, so by doing this offset function, my integral turns out to be really easy. And I just go to Mathematica, figure out what this is equal to. All right, I plug in my limits and I get this. This is just simplification. You can pause the video and go through this if you want. And here is a sub n. All right, so here are my a sub n's, and you're done here at this point. You can just do this. All right, that you can call that your answer. But I look at this and I realize for the even ends, this one's going to go to 0, and from the odd ends, this one's going to go to 0. So if I break this up into an odd and an even part, I can kind of simplify things a little bit more. All right, so here's what a sub n is for odd ends. Here it is for even ends. And then I just plug that into my Fourier series, and here it is. Here's my offset. Here's my odd amplitude. Here's my even amplitude. I sum all of those up, and summing this up to 100 terms, I get something that looks like the function that I started with. So it looks like I did it right.